Transmission lines, standing wave pattern, second part, series on transmission line theory, lecture number 2.21. When a line is terminated over an arbitrary impedance, reflections takes place at the load point. Interference between the incident wave and the reflected wave leads to the formation of standing wave pattern. In the standing wave pattern, voltage, current, and impedance, they all vary from point to point. In the present session, our focus is on impedance characteristics of the standing wave pattern over a lossless line. The line impedance at a distance x from the sending end in terms of sending end impedance Zs and Z0, characteristic impedance of the line, for a general line is given by this formula. Z. See, here is a line. General line means lossy line. At a distance of x from the sending end. This is sending end. At a distance of x, you consider a point P. At this point, line impedance. It is Z0, Zs. Zs is impedance here, sending end impedance, minus Z0 tan h, hyperbolic function. Gamma is propagation constant. X is distance of the point from the sending end, divided by Z0 minus Zs tan h gamma x. This is the formula. This relation can be obtained very easily by dividing voltage at P by current at point P. We have expressions for voltage at P. We have expression for current at P. We divided by I gives you Z. A little bit of manipulation gives us this particular expression. This expression, it transforms into the second one for a lossless line. In case of lossless line, what happens is gamma becomes equal to J beta. Substituting gamma equal to J beta, we will be getting the line impedance at a distance d from receiving end in terms of receiving end impedance and characteristic impedance for a general line can be found as Z equal to Z0, ZL plus Z0 tan h gamma d by Z0 plus ZL tan h gamma d. H means hyperbolic function, gamma is propagation constant. For lossy line, gamma is alpha plus J beta. For lossless line, alpha tends to 0. So in case of lossless line, impedance becomes Z0, ZL plus Z0 J tan beta d by Z0 plus ZL J tan beta d. So this formula is for impedance at a point over the line which is at a distance of d from the receiving end or load end. So impedance at a point P, line impedance, is given by these formulas. The connecting relation between line impedance and reflection quotient. This is the line, as already mentioned, when impedance, load impedance is arbitrary, forward wave exists, reverse wave exists. Now, reflection quotient can be defined at a point. What is a reflection quotient? Voltage in the reflected wave, you consider a point, an arbitrary point P. Voltage in the reflected wave by voltage in the incident wave. That is a reflection quotient. Okay, that is the reflection quotient at point P. At point P, one can define impedance also, line impedance. So at point P, reflection quotient is there, impedance is also there. These two can be related. Reflection quotient and impedances can be related. How? Using voltage and currents over the line at a distance d from the receiving end, in terms of receiving end current and impedance, the line impedance can be obtained in this manner. See, impedance at a distance of d, from the receiving end. At P, we have expression for V, expression for I. Now, V by I is Z. Z at D is Z0, ZR plus Z0 e power gamma D plus ZR minus Z0 e power minus gamma D by ZR plus Z0 e power gamma D minus ZR minus Z0 e power minus gamma D. Note, the first term is forward wave, second term is reflected wave. Here also, in the bottom also, first term pertains to forward, second term pertains to reverse. Now, you can do a little bit of manipulation. Divide both the terms by ZR plus Z0 e power gamma D. Then what happens? 1 plus ZR minus Z0 by ZR plus Z0. Similarly here also, ZR minus Z0 by ZR plus Z0. ZR minus Z0 by ZR plus Z0. This is the expression for reflection quotient over the load. Here reflection quotient. So impedance at point P, which is at a distance of D from the receiving end, is characteristic impedance 1 plus gamma L. Gamma L means reflection quotient over the load into e power minus 2 gamma D by 1 minus gamma L e power minus 2 gamma D. So this is the relation between impedance at point P in terms of reflection quotient over the load. Reflection quotient over the load is a parameter that can be calculated once you have ZR and Z0, which are normally available. So gamma L is known, Z0 is known, distance is known. Once you have this propagation constant, then one can calculate. Line impedance for a uniform lossless line in general is complex quantity, varying over the line periodically. See, the idea is simple. Point is, line impedance is periodic. This is the point. Periodicity is lambda by 2. It doesn't require huge amount of intelligence to understand this point. It has been told that voltage varies for the line periodically. Periodicity is lambda by 2. Current also varies with a periodicity lambda by 2. But impedance is ratio of voltage to current. When voltage varies with a periodicity lambda by 2 and current also varies with the same periodicity, naturally Z also varies with the same periodicity. Therefore, Zx plus or minus n lambda by 2 is Zx. Zd plus or minus n lambda by 2 is Zd. Line impedances at 2 points separated by distance lambda by 4 over a uniform lossless line are inversely proportional to each other. This is an important aspect with certain practical applications. You consider 2 points separated by a distance lambda by 4. They are inversely proportional to each other. Line impedances are inversely proportional to each other. So if it is more here, it is less. It is less, it is more. Line impedance assumes maximum value at locations where voltage is maximum and current is minimum. At the locations of V maximum and minimum values. Z minimum where voltage is minimum and current is maximum. The point is, Z is V by I. This fellow assumes maximum values when V assumes maximum value and I assumes minimum value. Fortunately here, understanding is quite simple. V assumes maximum value, I assumes minimum possible value at the same location. Therefore, Z assumes maximum value at that point. Now I can say Z maximum happens at V maximum or I minimum. Similarly, Z minimum happens at V minimum and I minimum. The consecutive locations where impedance is maximum are separated by lambda by 2, and similarly consecutive locations where impedance is minimum, they too are separated by lambda by 2, and the locations of Z max is separated from its consecutive J minimum by lambda by 4. Now these are the things which one can understand very easily. Locations of Z max fall over V max and Z minimum or V minimum. As two consecutive V max and two consecutive V minimum are separated by lambda by 2, so also two consecutive Z max and two consecutive Z minimum. Similarly, as V max and its consecutive V minimum are separated by lambda by 4, location of Z max is separated from Z minimum, next Z minimum by lambda by 4. Maximum value of line impedance tends to be infinity and minimum value 0 when the load is either OC, SC or pure reactance. Z is V by I. If I current assumes 0 value, Z becomes infinity. I minimum, V maximum. If I minimum is 0, then Z is infinity. I minimum is 0 when termination is OC, SC or pure reactance. So in this case, only in these three cases, Z is infinity. Maximum value of line impedance Z max tends to infinity and minimum value Z minimum becomes 0 when load is either OC, SC or pure reactance. So in such case, Z max where it happens is at V max, there I minimum 0, therefore infinity. Z minimum happens when V assumes V minimum value, Z assumes minimum. When V is V minimum, I is I maximum. In such case, it assumes 0 because V minimum is 0. Then at both the locations of V max and V minimum, line impedance for lossless line is pure real. Note, this is an important point. If you plot Z, it assumes maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. Similar to voltage. Voltage also same thing. maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. Almost same. Now, what he says is the maximum value Z max can be found to be Z naught into rho. So here, what is the impedance? It is Z naught multiplied by rho is standing wave ratio. At minimum, it is going to be Z naught by rho, irrespective of the termination. The minimum line impedance and maximum line admittance are related through Z minimum equal to Y max. Within a distance of lambda by 4, the line impedance is inductive on the left side and capacitive on the right side of any V minimum. See, consider voltage pattern. This is V minimum. What he says is left side within a distance of lambda by 4 and up to this point. Within a distance of lambda by 4, within this distance, line impedance is inductive. Left side it is inductive. Right side it is capacitive. It is capacitive impedance. So here is shown A. In A, this is the line. You consider 2 points A and B. A and B, they are separated by integer number of half wavelengths. What he says is, when the distance between them is integer number of half wavelengths, ZB is ZA. These two impedances remains same when the distance is integer number of half wavelengths. When the distance between them is integer number of half wavelengths plus lambda by 4, then in such case, ZC, that means impedance here is Z naught square by ZA. ZA and ZB. Point is this, A to B, this line is a half wavelength line. Half wave line. This is called half wave line. A to C, it is called quarter wave line. The properties of these lines we study under line sections. There we can find the impedances of terminating impedance. ZC is Z naught square by input impedance ZA or ZB. Now come to figure B. Z max here is shown. It is given by Z naught rho. Rho is standing wave ratio. Z minimum is Z naught by rho. Here you can see between minimum and maximum. Z minimum and Z maximum, the distance is lambda by 4. Between two maximum, it is lambda by 2. Another thing is at maximum and minimum, impedance assumes real values. Real. At maximum point it is real. At minimum point it is real. But maximum it assumes high value. At minimum it assumes low value. Left hand side it is inductive. Right hand side it is capacitive. Z max tends to infinity. Z minimum is 0 when ZL equal to short circuit, open circuit or pure reactance. Some more information. Maxima and minima and reflection quotient. The relation between voltage maxima and reflection quotient. The relation between voltage minima and reflection quotient. The relation between current maxima, current minima and reflection quotient. Similarly, line impedance maxima, minima and all. V max is given by V plus 1 plus gamma. V minimum is V plus 1 minus gamma. I max. I max is V max multiplied by Y naught. I minimum is V minimum multiplied by Y naught. Similarly, line impedance. Line impedance Z, consider a line. You consider a point. At this point, Z exists. At this point, gamma also one can calculate. What is the relation between Z and gamma? The relation is Z is equal to 1 plus gamma by 1 minus gamma. Note small z. Small z means it is normalized impedance. Small letters indicate that it is normalization. Bold face Z means it is complex quantity. Similarly, gamma also. Gamma here is bold face, means it is complex quantity. So relation between Z and tau is Z equal to 1 plus tau by 1 minus tau. This is gamma. Yes, gamma. Z is 1 plus gamma by 1 minus gamma. Gamma is Z minus 1 by Z plus 1. Z max is 1 plus gamma by 1 minus gamma. Here it is simply magnitude. Z minimum is 1 minus gamma by 1 plus gamma. It is 1 by rho. Rho is standing wave ratio. Now, while implementing load matching techniques, we need to know the distance of voltage minimum or voltage maximum from the load. Here we are trying to find out distance of first voltage minimum from the load. It is indicated by D minimum. D minimum in case of capacitive loads. It is illustrated in A. D minimum in case of inductive load. It is illustrated in B. In case of capacitive load, this is load point. This is first minimum. voltage minimum, the distance between them, D minimum. It is evaluated considering this particular diagram. In B, inductive load. Inductive load means load point is somewhere here. First, what you have is voltage maximum, then voltage minimum. The distance between voltage minimum and load point. What is this distance? To calculate D minimum, these diagrams are useful. What is the idea? The basic idea is gamma reflection quotient varies 180 degrees or pi radians when you move from voltage minimum to voltage maximum. So the variation in between these two, voltage minimum, voltage maximum, is 180 degrees or pi. But the distance between voltage minimum and voltage maximum is lambda by 4. Therefore, lambda by 4 corresponds to pi. Pi, or pi corresponds to lambda by 4. Let us suppose angle of reflection quotient is known to us. Let us suppose it is theta L. When pi corresponds to lambda by 4, what is the value of distance that corresponds to theta L? That is D minimum. From this logic, D minimum is calculated. When termination is inductive, Vmax exists nearest at a distance of lambda theta L by 4 pi from the load. Then V minimum is a V minimum at lambda by 4 farther away. However, when the termination is capacitive, V minimum exists nearest at a distance of lambda multiplied by pi plus theta L divided by 4 pi from the load, and then Vmax at lambda by 4 further. In either case, D minimum, the distance of V minimum from the load becomes this one. D minimum is pi, theta L is angle of reflection quotient over the load, lambda by 4 pi. This information regarding the location of voltage maxima, voltage minima, it is placed in a tabular form. When load is capacitive, minima distance, first minimum distance you get when n equal to 1. When load is inductive, distance of first minimum by substituting n equal to 1 here, you will be getting. When load is capacitive, distance of first maximum you will be getting by substituting n equal to 1 here. When load is inductive, first maximum distance from the load you can find from here. When load is resistive, more than Z0, resistive less than Z0. That information is provided here. This is what I want, or I have with me to share with you.